dielectrics. Capacitors measurement. So again, many things you know, and you are teaching electromagnetic theory, they must be teaching all these things, dielectric materials. So we will start with how you classify the material. Either it can be conductor, semiconductor or insulators. So what do you mean by dielectric material? It's electrically non-conducting material. But how you differentiate them, insulating and dielectric? The purpose for which it is used. If you are using for insulation purposes, it is insulating material. If you are using it to store charges, like between the capacitor plates and so on, then it is called as the dielectric material. Now this dielectrics also can be, material can be divided in further into different categories, where we have some material which have permanent dipole moment and some which do not have permanent dipole moment. Consider benzene. Think of that ring. It's perfectly symmetrical, so there is no dipole moment. There is no permanent dipole moment. That means it is a non-polar molecule. So that is one group. And the second group, where you have dipole moment, like H2O, which has the oxygen and hydrogen. They don't form a neutral thing. So there is a slight charge towards hydrogen as well as towards the oxygen. So that is a polar molecules, and they behave slightly differently as dielectric materials. And very important thing in dielectric materials is the polarization. So what is polarization? So when I apply external electrical field, under the influence of that, there will be a dipole moment created. We call induced dipole moment. So if there is a induced development of induced dipole moment, it is called polarization.
Induced dipole moment are indeed only.
Yes.
Are indeed only.
I am talking of process, not the vector P. That polarization is vector P. Then you talk about dipole moment per unit volume. I am talking of what is polarizability. What is polarization process? I will come to that. So now, this polarizability will depend upon the external applied electrical field. More is the field, more the charges will be displaced, more dipole moment, and hence I say that since my dipole moment is proportional to the applied electrical field, so mu is equal to alpha E. This alpha is the polarizability of the atom or molecule. Now this is the property of individual atom. Here it measures what? How easily you can polarize that. Polarizability will be the measurement of ability of the material to get polarized in the presence of external field. This thing will happen in both, whether it has permanent dipole moment or not. The polarization will happen in both type of molecules. Now there are different types of polarization. We will be discussing 3 of them, which are more important, that is electronic polarization, ionic polarization, orientational, and last is phase charge polarization. Out of these 4, there are 2 processes normally happens in the nature. One is relaxation and the other is resonance. That is the absorption of energy. In electronic and ionic, it is going to be with all four. First is electronic polarization. So what happens in this case? You consider an atom where you have positive charge center and a negative charge center coincides. So that means there is no dipole moment, or there is the centers of positive and negative charge are not displaced. But as soon as I apply the external electrical field, since the electrons are lightweight, they will be displaced slightly towards the positive side. So I have this electrical field 0, this is the position, and when I have this, see, it will be like this. This is this center. Yeah. Actually this green part also should be here. Okay, that's while adjusting I think it's shifted. So sorry for it. This also should be here exactly. And when I apply the field, the negative goes towards the positive plate. So it is the electron cloud which gets displaced. And now you can see a positive and a negative charge which are at a very small distance, they form dipole. So they will have dipole moment. So we will derive this equation also. Then we have ionic polarization where we have ionic bonds. So we know that where I have ionic bonds, I will be having a slight shift of positive and negative charge, okay, depending on the electronegativity of that particular atom. So I have like this one molecule having positive charge center, negative charge center. Second molecule, third molecule like this. So it is within the molecule I have a positive charge and the negative charges. That means they have a permanent dipole moment. Now what will happen if I apply external field? Here, though there is a dipole, but they are randomly distributed. So, if I talk of the material, there is no net dipole moment. Okay, only when I apply the electrical field, negative charges will be shifted on one side, positive on the other side, and my material will get a net charging. One positive, one negative, and here my dipole moment will come into picture.
Would there be change in crystal structure also?
It's very small. Very small. It depends upon actually the frequency and the amplitude.
The way you have shown that this is charges.
So that is for understanding. It's not going to happen. Like you take oxygen, H2O.
Even H2 is already, but sodium iodide is a crystal and its structure will change every.
This is very amplified.
There no change in the equal size, no change in the electronic orders. Under the pressure of
Yes, so
only
only
the
cloud. So positive and negative charge centers we are talking.
central vacuum shift.
Center. We are talking about
Suppose we take a crystal which is purely centrosymmetric. A crystal structure dictates that whether it can have a dipole moment or not. Right? Crystal symmetry plays a very important role. Take the example of barium titanate. It is a classic ferroelectric crystal. But at high temperatures, the structure is cubic, in which the center of symmetry of both the positive and negative charges coincide. There is no permanent dipole. But you cool this crystal at a characteristic temperature below 120 degrees Celsius. 120 degrees. The structure gets distorted to a tetragonal type. So one, then you will have a displacement of a positive and a negative charge. That gives rise to a characteristic dipole moment. So these dipole moment and symmetry, they are very, very important. Whether for a given crystal it can have or not, even without doing an experiment, I can tell if it is like the cubic symmetry, it won't have. Tetragonal, it will have, because there is one direction, different from the rest, right? There is no center of symmetry. So these are our transitions. In fact, one of the experiments we have kept it in material. We also have a refresher course which we have just started in material science. For all it is physics. Material science is also physics related. So we study as the teachers or the student to study one transition. And how do you study this transition? Is essentially study through the dielectric constant. You measure the dielectric constant of a material. And how do you measure the dielectric constant of a material? It's very simple. Probably we teach in high school or probably in college physics that you take a parallel, you make a parallel plate condenser. Take two parallel plates. Take the material in between of your interest. Make a parallel plate. That means, or you take your crystal in whatever form you have got and then coat it, metallize it, both the surfaces, and then study the capacitance. See, through a bridge, same thing, it's related. We study bridges. What is the idea of all these bridges? Is to finally make a measurement. You want to have a measurement of, say, capacitance of what you want to measure. Just study through this bridge. So there are professional equipments called LCR meters. It is, you measure everything, all the impedance, L, C and R. R is the simplest thing we go to. But you also measure and see. It is an AC thing. And all this nulling, everything like that under different engineering, it is done inside in an automated way. Now, these are no manual things. It is inside. The logic, that is your final condition that it has to be null is given. And then the components adjust in such a way that that null condition is there and you directly measure capacitance. Now, you measure capacitance as a function of temperature. You have got all the phase transition. In fact, I can show you some.
They have it.
No, they don't. They have an experiment on probably you are teaching them. No.
I am thinking that liquid.
That's liquid, yes, fine.
That is what we
Yes,
are
in fact, finally, probably the most important thing, like what she mentioned here, is the concept of polarizability. Finally, polarizability. How do you displace the charges to an external electric field that depends on the interatomic forces? How the electrons are bound to the nucleus. Suppose the bonding is very, very strong between the electrons. Then
Answer is the question.
Answer is different.
So, another question. Suppose we keep the temperature constant, right? And I apply electric field to a crystal. It gets polarized.
yes.
Would there be a change in its crystal structure also?
Is there change in the nucleus?
Would interatomic distance get
Would have
change
change
in the layers?
No. See,
This is my question.
Addition of nucleus. You are talking about addition of nucleus.
So what is the change or not?
How?
Like if I
what you are asking is a question. Like, can an external electric field probably?
Yeah.
But this happens only when the fields are very high. Very high. You can make a system just by field itself to change the symmetry of the system. Like whatever you asked, the symmetry of it. This is a strong field, but usually if you take the normal fields, they are so low compared to these.
But there will be ionization.
Yes.
Dipole is greater. When
Yes.
I use dipole,
You can create this dipole.
Dipole moment will be induced.
Yes. Yes. Dipole
Is there change in the orbital structure or?
it can be there, but provided the fields are very high. Usually it doesn't be.
because the displacement of the charges is very, very small
Extremely small.
compared whatever the bond lengths.
Yes.
Then we have to modify that to a diagram.
Yes.
We have to modify that diagram.
Electrodes, that's what I say, electron cloud will be.
Shape is changed, orbit shape is
Many
changed.
times you bring about this type of dipole moments induced by crystal, just by changing the symmetry of the crystal by an external agency like temperature. Just the temperature itself makes some crystals to go over from a perfectly symmetrical one to a non-centrosymmetric system in which it can have a dipole moment. So, the existence of a permanent dipole moment or not is primarily dictated by the symmetry of the crystal. And if I change the symmetry by temperature or any spin, you can have things. That's one of the issues.
The next important one is the orientational polarization. So as name suggests, it will be orientation of the dipole moment. That means I have polar dielectric now. There are already dipole moment exist, but because of temperature, they are randomly oriented in all different directions. So net dipole moment is still zero. But when I apply external electrical field, it will try to orient my dipoles in the field direction. It will exert torque on this. There is a permanent dipole moment already existing. It will experience the torque, and therefore you will see that there is net induced dipole moment coming here also in picture. It is H positive and here H minus and plus. First one. Minus
Positive
and
here
plus.
the medium है positive here.
Now this is space charge polarization. Normally it happens in heterogeneous where symmetry and all that stuff was talking, and then symmetry is broken after a certain distance. It's not a perfectly similar structure in the entire material, and in those cases it comes into picture. And it's important only at very low frequencies. So normally we don't talk about this. We talk about the remaining three. That is, my polarizability will be function of three things. One is the electronic polarizability, the ionic, and orientation. So we will try to find out. So this is in short all the processes. The same thing. So what happens now? There is external applied field, and therefore there is an induced dipole moment. And hence at a given point, if you see, there will be an internal field that acts on the site of that solid, the site of the atom. It is, we are going to take liquid, and that's why I have mentioned here liquid. That means that when I am talking of now electrical field at a point in a dielectric, I have to talk of both the things, the external electrical field as well as the induced field because of polarization. So these two fields will play the role, and that is my actual electrical field. So now let's go for some definitions, and then we will derive that equations. So what is dielectric constant? polarization part can also be given in terms of height, that is susceptibility of the material. This comes because my polarization will be proportional to the electrical field and proportionality constant is taken as epsilon naught and phi t. This epsilon naught can be taken out. So I have this equation for D. And we define the relative permittivity or what is called as the dielectric constant of the material. In some books they write K, some books it is written as ER, epsilon R. That is epsilon by epsilon naught and which is 1 plus I. Now this quantity always comes when we are talking of what is the behavior of a material in an external electrical field. So you must discuss at that time nothing but this dielectric constant. So after measurements, you take dielectric constants and based on that you discuss how my material is behaving.
Ma'am, how do we define permittivity? So we understand it that it is a material property, but if we are asked to define it, how to define it?
Define it, its definition comes from the force between the two charges, that F is Q1 Q2 upon 4 pi epsilon naught R square. So from there the factor on the proportionality constant was taken as 1 by 4 pi epsilon naught. The force between two charges is proportional to the product of charges and inversely proportional to the distance square. In CGS unit it is fine, it's kept as it is. But to adjust the MKS unit, the constant was taken as 1 by 4 pi epsilon naught, and that is how the epsilon naught came into picture. Sir may tell you different story. That's all.
On the material type, not select, not
Epsilon naught. She said from there is the that is how it's.
generally for the medium take
Then you take epsilon.
different.
What is the force experience between the two charges? From there, this was introduced.
Even we cannot define it in terms of electric fields.
Yeah, how permission it gives.
How much permission the medium is giving to react, to interact with the
Permission may be in terms of electric permanent charge electricity.
She is not asking a formula. Physical definition. Physical definition. The formula is different, na? But physically, how would you define it? What formula?
In the question, as I
How do we define the absolute permittivity? How do we define the absolute permittivity for its physical significance basically?
you require, suppose, like you require certainly a medium.
Yes.
A medium material is required for the odor.
Given by the medium.
But there is
We are talking
this is
about
polarization
absolute absolute in vacuum.
In vacuum, that's what. See, vacuum earlier when the Maxwell said the earlier time, because for all electromagnetic interactions, it was considered as a medium which was called ether, which was a medium, it had some special properties which is like that. So, but now we know that electromagnetic radiation can propagate even in vacuum, but then this concept, this vacuum itself has got a polarization, that is the vacuum. That means this electromagnetic field which is there even in free space, there is, like in quantum mechanics, you have got what are called as half H. These are called the 0 point energy of the electromagnetic field which is there. So this concept, even though it is ideally there is nothing, it is filled with an infinite amount of energy, but each of quanta of half H. You can't really use it for any thing because all of them are only half the quantum. So this type of vacuum polarization which is the effect which is that produces on the medium, is the one which gives rise to that. So this part of epsilon, if you want to do fundamentally, is one of the important contributions in a field called quantum electrodynamics, QED, quantum electrodynamics. This part is now done as a fundamental. In fact, wherein we just ask even simple questions like what is the structure of even an electron? We think of even an electron as something which has got a structure, and what is the characteristic length associated with this? It has got something finite, nothing is zero. Suppose it is like an amount of charge distributed over like a sphere. You can imagine that the distances are so small, if it is all like charges, they will repel and explode. It's not what binds this. What is this? These are the questions which are asked. For us, we assume there is an electron with a charge, simple, connected. But if you want to know the real structure connected with it, and then what is the field produced by an electron itself, these are something like, if you read probably Feynman lectures, the second volume, there is a very nice discussion on this structure here. So these are things which are related to things like vacuum. Vacuum, we think there is nothing. That's one way, like vacuum. That is, we are in a vacuum means that actually there is nothing. But vacuum has got a lot of energy associated. It is that energy which we cannot physically realize because it is all hot quantities. But you see the effect of this vacuum in some of the energy levels of hydrogen itself. If you do, it is something which is a nice effect which comes about, that the vacuum field perturbates the field of the shells, S1, S2, P's and all these things. And the small amount of chips which we get was experimentally discovered and proved that vacuum has got its own polarization. We call it as vacuum polarization. So that is the one which is fundamental. Coefficient it comes out automatically. If you want to calculate those magnitudes.
The question was asked
Now we will try to find out
the
what is.
question was different.
That means question was slightly different.
Or we use it only in SI units.
Yes.
We don't use it in CUs.
Nowadays we
So
do.
is it some correctional quantity or it has something intrinsic to do with that? That was the question.
Not experience. It is with any medium. That's not going on everywhere. Whether it is medium or not, but in vacuum it's the that is the effect of the medium on the forces.
But when using SI units, we use it.
See,
Not when
when I understand in that way, if I have forces, what is the force experience also depend on the medium. So the medium effect is taken out in the and then they should not be independent.
Coffee is ready. I believe coffee is ready. I think probably we must practice